Here we are. It's at the top of the hour. I see everybody jumping on. Ahmed, if you're set to go, maybe we'll go ahead and get started here. With that, let me welcome you all to today's Aspire Brown Bag presentation. I'm David Christensen, the Innovation Director for Aspire, which is an NSF-funded engineering research center. It's very much my pleasure to introduce you to our Aspire special guest presentation or presenter today, Dr. Ahmed Mohammed, who is a senior IEEE member and research engineer in the Advanced Vehicles and Charging Infrastructure Group at NREL. Now, I'll ask Ahmed to further introduce himself and his topic here in just a moment. We'll proceed with today's presentation for about 30 minutes, after which we'll have time for some Q&A and discussion. First, let me remind you that we're recording this session to post later on the Aspire website. When we get to our Q&A and discussion, you'll be able to open up your mic, or you can send questions through chat. You can even do that as we go on the chat feature if you like. So, Ahmed, with that, I will turn the time over to you for your presentation, and we look forward to it.
Perfect, Dave. Thank you for the introduction and inviting me to this meeting. So are you able to see the slides?
Yes, right now it looks like we're looking at your presentation notes. Maybe we're not on the right screen.
So just
There we go. Looks good.
Is it better now?
It's not in presentation mode yet. Oh, now we're back to notes. Unless you have animations, you certainly could keep it in presentation mode, whatever your preference is.
I don't really have animation, but I like also to have it in the presentation mode.
Right.
So. Is it better?
Well, no, we're still seeing your notes.
So let me stop sharing and share again.
Okay, great. It looks like everybody's still jumping on. We still have a few more joining us, so you're fine, Ahmed. We'll get this.
Is it okay now?
That looks good.
Okay, perfect. Should we start?
Yeah, I don't. Looks like you have some voice recognition text coming up down at the bottom, which you may not want. But if you want that for captions, maybe that's okay. We'll let you go ahead.
Okay, thank you. Thank you, Dev, again for the introduction, and thank you everyone for attending the presentation. So my name is Ahmed Mohammed. I'm a research engineer at the National Renewable Energy Lab. My background is power electronics with focus on charging infrastructure and electric vehicle. And today my presentation is about system planning for charging infrastructure, and we're gonna focus on one of the transportation mode, which is fixed route automated vehicles. And we're gonna try to present some insights about the comparative analysis between stationary and en-route charging technology. The outline first, I'm going to introduce brief introduction, give a brief introduction for EV charging technologies, and then I'll present the challenges related to system planning and optimization. After that, I'll discuss a case of study for a real project at the University of Michigan that has automated shuttles. And after that, I will present results and conclude my presentation. In this work, we focus on road transportation, which include private vehicles, taxi, transit buses, commercial trucks. And we depend on transportation not only to get to work, but also to shop, socialize, access healthcare, and among other goals. However, the current transportation system experience some challenges in terms of cost, safety, adequacy, environmental impact, and also time wasted. And also at the same time, we see three main revolutions that are currently happening in the current transportation system, which I call them game changers. The first revolution is the electrification, to electrify vehicles. And the electrifying vehicles mean less fossil fuel use, less emissions, more adequacy, and also less cost. When I mention cost here, of course, this include operating cost like fueling and maintenance, but also in some cases it might include capital cost. How this happen? If you know that a lifetime for an EV around 2.5 times an ICE. So if you are a fleet, so instead of having 3 ICE vehicles, you can have just one electric vehicle to do the same job. Of course, you need to account for battery life, but I think at the end it might end up with saving for fleet owners. The second revolution is related to automation, which mean to have the vehicle self drive itself. And it might help to make the transportation system safer and also to save the time wasted in the transportation. The third revolution is shared mobility, and I think this is get impacted a little bit by the current dynamic, but by the current pandemic. But I hope this is a temporary situation. And the sharing mobility concept is a concept that make perfect sense. The simple reason is that about more than 95% of the time our vehicles are parked. So it makes sense to try to get benefit from this vehicle while they are not used. So sharing mobility mean less number of vehicle, less traffic congestion, less parking issues, and also less travel time and less energy consumption, and of course less cost. So to share vehicles, I think is gonna be much cheaper than to own a vehicle. However, in order to see the full impact of these revolutions in the market, there are still some challenges that need to be tackled first. Challenges related to the vehicle in terms of cost, in terms of range, driving range, and also if we're gonna talk about automated vehicle, so we need to see a reliable vehicle that can drive at high speed safely in the road. Also, we have challenges related to infrastructure, including charging infrastructure, road infrastructure, signaling infrastructure, and also challenges related to regulations. We need to get approval for this vehicle to run on our roads. Today I'm not going to talk about all these challenges, as I'm not expert in all of them, but I'm gonna focus on challenges related to electrification for vehicle and also charging infrastructure. So I see we have four main challenges related to electrifying vehicles. The first challenge is about the driving range and anxiety. The second is the long refueling time. We see much longer than to recharge a vehicle. It takes much longer than to refuel an ICE vehicle in a gas station. And the third challenge is related to cost. Not everyone afford to own an EV. And the last challenge is related to availability, charging availability. So we don't see a charging, or we don't find a charging station everywhere as we see in a gas station. And when we look at the way that people try to address these challenges, we see two different directions. One direction suggests to try to increase the battery in the vehicle and to target a specific driving range, and at the same time to install stationary charging infrastructure to allow for target charging time. However, increasing the battery in the vehicle mean more expensive vehicle, higher energy consumption, and also we're still talking about limited range, whether it's 300, 350, 400 mile, but still limited. Also, even with the faster charging technology, we see a charging time range from 20 to 30 minutes, which is still much longer than what we see in a gas station. And of course, this infrastructure is not so cheap, so it's gonna cost a lot of money. The other directions is to the suggestion is to try to optimize the battery in the vehicle and try to use a smaller battery and attach this with en-route charging technology. Of course, reducing the battery in the vehicle will help to reduce the vehicle price and also lower the energy consumption. And attaching this with en-route charging technology. First, let's what is en-route charging technology is a technology that allows the vehicle to charge while it travels. So this can be during the transient stops like traffic signals or bus stops, or also it can be during movement on highways. So with appropriate design for this technology, we theoretically we can allow unlimited driving range for the vehicle and also to realize zero refueling time. However, also this is technology is not so cheap and it involves a lot of component and we need to plan for it. So in this comparison, I'm not trying to say one solution is better than the other, but my expectations that we're gonna see the two technologies. However, the important question is which one make more sense for a specific application. And I think the answer will be different based on this application. For en-route charging technologies, we see few options for this technology. It can be overhead transmission line with a pantograph, or it can be a rail with a sliding arm on the surface of the road, or also on the side of the road, and also it can be wireless charging. And when we talk about automated vehicle, I think wireless charging is a strong candidate for en-route technology. First, wireless is automatic in nature, so you don't have to add any extra component to the system to make it automatic. Also, wireless is flexible, so you can have it on the road, you can have it in a station, you can have it in a stop, since the system is embedded in the road. And with appropriate design for the system, we can make it interoperable. So the same system that you have for a bus can be used to charge a small vehicle, which is not the case for a pantograph, for example. Pantograph typically designed for large vehicle, and the small vehicles cannot use it. And finally, wireless is reliable in harsh environment and extreme weather conditions like heavy rain, wind, or snow. So what do we mean by planning for the system? As we might know, the wireless charging involve two parts. One part has to go to the vehicle, and the other part has to be in the road. And these parts involve expensive wires like lead wire, ferrite material, shielding, power electronics, expensive capacitors. And also this include the vehicle part and also the road part. So in order to make the system cost effective, we have to plan for it before building the system. Another challenge related to en-route technology, it's a kind of coupled problem. We cannot size the vehicle by itself and then go and size the charger separately as we can do for a stationary technology. But in this case, the performance of the system depend on vehicle and the charger together. And this coupling relationship, we can see it from the figure on the right side, which shows the relationship between charger power battery size of the vehicle, and also roadway coverage. Roadway coverage is a percentage of the roads that we need to electrify as relative to the total length of the road. So the figures show that increasing the power level of the charger can significantly reduce the length of the road that we need to electrify. And of course, reducing the roadway coverage will significantly reduce the overall system cost. So we don't have to do a lot of construction work and installation work on the road. Also, reducing the battery on the vehicle mean reducing the vehicle cost. So it seems like increasing the power and reducing the battery is the most cost-effective solution. However, this is not 100% true. Since increasing the power and reducing the battery is gonna end up with a very high C rate for the battery, which can be challenged for the current battery technology to handle this high C rate. And even if we have the technology, this technology is gonna be is not going to be so cheap. So with this kind of the trade-off between the cost and performance, that's why it's really important to try to plan for the system before start building the hardware. So our goal is to try to address four main questions. The first, what is appropriate roadway coverage? What is appropriate power level for the charger? Where to place the charger in the route, and also what is appropriate size for the onboard battery. And in order to answer these questions, we developed a tool at NREL. It's an internal tool that has a powertrain model for the vehicle, and also it has a charger power model that account for misalignment in travel and lane directions. And these two models are used to predict the battery power, energy, and the state of charger profile. And the models receive real-world data, travel data, speed profile, grade, road grade, and try to use this data to evaluate the performance of the vehicle. And the tool also has a second layer, kind of optimization layer, that has cost model for the system and an automatic search algorithm. So this optimization layer receive output from the energy estimation layer, try to evaluate objectives and constraints, and regenerate optimization variables that we are interested in, and keep this loop until we have optimal solution. This tool is appropriate for small scale scenarios like a fixed route shuttles or transit buses, on demand shuttles. However, we have an updated version for this tool that deal with large scale deployment of the system on roadways. Imagine a city or a state that want to implement dynamic charging on primary roadway, and we need to plan for the system first, and then evaluate how the system will impact the travel performance within the city. So this is another update for the tool, and the tool has the capability to do that. However, today for our case of study, we're gonna use the simple form of the tool. So the project that we are focusing on today, it's a real project at the University of Michigan that has two automated shuttles, Navia Irma automated shuttles. They run in a circulator in a fixed route, and you can see the route in the right-hand figure. It's around 1 mile route, and the route has two stops, south stop and north stop. The vehicle is supported by a 33 kilowatt hour battery, and also it has on board the level 2 charger to charge overnight at the garage area. Our partner in the project from the Idaho National Lab collected data from the vehicle related to energy and also travel data. And we leverage this data in this project to plan for charging infrastructure for this vehicle. So first, we start to use the data to accurately model the vehicle due to the uncertainty in the auxiliary load estimation. So our result shows a range of from 4 to 5 kilowatt auxiliary load, which accounts for AC, cameras, sensors, radar, and processing and other. This number are quite high compared to a regular vehicle, and we expect to see a lower number in future. Also, we use the travel data to see how the current vehicle behave, what's the performance of the current vehicle. And on the right side, the bottom figure shows the state of charge profile for all vehicles over 60 days. As you can see, the average range for the vehicle changed from 5 hours to 6.5 hours, continuous operating hour. So for this vehicle to run for 12 hours, for example, or longer, as it's intended for automated shuttles, I think something needs to be done with this vehicle. So the question is, what are the options? What we can do? The first option is to consider the current technology in the vehicle, which is level 2 charger, and to try to increase the battery in the vehicle to run for 12 hours. The second option, if we want to test, if we want to try DC fast charging technology, so we can install one unit for DC fast charging and to charge the vehicle within 15 minutes as a target charging time, and also to increase the battery to allow for 12-hour driving range. The third option is to look at en route charging technology. And in this case, we have two options, either quasi-dynamic or dynamic. Quasi-dynamic, we're gonna target the stops, the south stop and north stop, and try to evaluate two or one charger at one or two of these stops, and see if this will be enough to allow charge sustaining for the vehicle. And of course, the last option will be to cover or to electrify part of the road to account for dynamic charging technology. So these are the four options that we investigated in this project, and we try to compare between all of them. As I mentioned, we are interested to define number and location of a charger power, and the length of the charger at each location. If we're gonna talk about wireless charger, and also the battery size in each case. And our objective is to try to minimize the overall system cost, which include road component cost, and this one accounts for power electronics, material, construction work, installation work, and also grid connectivity. And the vehicle component cost, and this one accounts for battery as a function of capacity and the charging rate, and any electronics that has to be in the vehicle, like a vehicle assembly for wireless or onboard the charger, if we consider level 2 AC charger. And we have some constraint related to charge sustaining. Charge sustaining mean to have almost or near flat state of charge profile, which theoretically mean unlimited driving range and zero downtime. So we have this objective or constraint for en route charging technology. However, we cannot achieve this constraint for stationary technology. So our constraint for stationary technology is to have 12-hour range and 15 minutes for DC fast charger and 8 hours for level 2 charger. And there are other constraints related to battery technology like C-rate limit and the state of charge. And due to the uncertainties in this technology, it's a developed technology. So we have to do assumption related to cost and also related to a vehicle. So we run two scenarios. One scenario that include assumption for present day, which account for present day cost for material, power electronics, construction work, and also account for the current vehicle, present day vehicle, which was inefficient operation. And also we run another scenario that we call it future, that account for futuristic assumption for cost and also vehicle. And here are the results. These are the results for en-route charging technology. As you can see, we have present day scenario and future scenario. And for under present day, we have quasi-dynamic case and also dynamic case. How we can read these numbers? For quasi-dynamic, we see two optimum solutions. For example, solution S1, the suggestion is to have two chargers, one at the north and one at the south stop, and each charger is 50 kilowatt power, and we just need one bed of wireless charger. We don't have to cover long length of the road, but we just need one bed of transmitter. And in this case, 29 kilowatt hour battery should be enough to show charge sustaining operation. Another optimal solution suggested to have just one charger at the north stop, and this charger is 100 kilowatt power level. And also in this case, we don't need long coil, but just one bed is enough, and the battery size 28 kilowatt hour. When we run the dynamic scenario, it provides the same solution as quasi-dynamic, which is, it makes sense if you are able to charge the vehicle at the stops, so there is no need to electrify the road. And it seems like quasi-dynamic shows the most cost-effective solution. So that's why we see the same solution when we run the two scenarios. For future scenario, we see much lower power because of the assumptions that we have more efficient vehicle, and also we see lower battery size in the vehicle. And these two figures shows a comparison between a vehicle running without en-route technology, en-route charging technology, and a vehicle running with the considerations that we have one charger at the north stop with 100 kilowatt and the 28 kilowatt hour battery. So as you can see in the right side, we see a near flat state of charge profile. This is what we meant by charge sustaining operation. And this is, we can theoretically assume that this is gonna provide unlimited driving range, and the vehicle doesn't have to stop for recharge. While in the left, however, in the left side, we see the decaying profile if we have the vehicle running without any en-route charging technology. So, and these are the number for stationary technology, also for present day and future scenarios, including DC fast charger and level 2. So if we need to have 12-hour battery, we need to 12-hour operating hour, we need to install 70 kilowatt hour battery, which about 100% more than the current battery in the vehicle. And one DC fast charging unit at the garage with 250 kilowatt should be enough to charge the vehicle within 15 minutes. If you consider level 2, we need 2 units. And each unit 8 kilowatt, and these 2 units will charge the 2 vehicle within 8 hours. Also for future scenario, we see a lower battery, almost half, and also lower power level because of the efficient vehicle in this scenario. So this is a kind of comparison between the 3 options en route, DC fast charging, and level 2. The figures in the left and the right side shows the state of charge of the vehicle, considering the 3 technologies. One figure for present day and the second figure for future assumptions. The solid line shows the vehicle with en-route charging technology, which both vehicles shows almost flat state of a charge profile, and this run for 12 hours. However, for stationary technology, whether level 2 or DC fast charging, we see almost 12-hour operating 12-hour driving range as we run the numbers. And we see similar also performance if we consider future scenario. The table in the left side, in this table, we try to compare between the three options. Quasi-dynamic, at the end, we might have unlimited driving range and zero downtime. DC fast charging, we have 12-hour range, and the vehicle is gonna need 30 minutes to charge the two vehicles. And also level 2, it will have 12-hour driving range and 8 hours to charge the two vehicles. When we look at the cost, vehicle component cost, road component cost, and overall system cost, I'm showing the costs here as a fuzzy number. However, these fuzzy number derived based on real number, considering the assumptions that we have. So for vehicle component cost, which include batteries cost plus the power electronics that have to go to the vehicle, DC fast charger shows the highest cost. Why is that? We have large battery, 70 kilowatt hour, and also this battery has to be charged at high C rate due to 250 kilowatt charger. Even though for level 2 we have the same battery size, but this battery will be charged very slowly, less than 1 C rate. So the battery will be the cost of the battery will be much lower than the batteries that need to handle high C rate for DC fast charge. Quasi then in the en-route charging technology, we see medium number. For two reasons. Even though we have a smaller battery, but this battery has to be charged at high C rate, so the battery is not so cheap. Second, a vehicle assembly has to be installed in the vehicle. That's why we see a lower number than DC fast charging, but also it's a little higher than level 2. For road component, DC fast charging shows the highest number because it's the highest power, 250K. But en-route technology shows a medium number, it's only 100 kilowatt. And level 2, of course, shows the lowest number, it's only a 2 unit, 8 kilowatt each. So when we add these two components, we end up with DC fast charging shows the least cost-effective solution. Quasi-dynamic is much lower than the DC fast charging technology, but also it's a little higher than level 2 charging option. Besides the cost, we know wireless charging is automatic, so you don't have to hire someone to plug in and plug out the vehicle. Also, with lower battery in the vehicle, you can save some money from the fueling due to the low energy consumption. So in general, in conclusion, with about 15% reduction in the battery, along with installing en-route charging technology, the vehicle might be able to realize unlimited driving range and zero downtime. If we compare this with a stationary technology, so you have to increase the battery in the vehicle by more than 100%. And also, this will enable only to double the driving range. DC fast charging technology is not the best option for this application, given the assumptions that we have in this study. Also, a quasi-dynamic solution are much more cost-effective than DC fast charging, and also more convenient for automated vehicle than level 2, which is not automatic. So I think this is the last slide that I have, and I'm happy to receive questions.
Yeah, Ahmed, fantastic. Great presentation. I know that there's some going to be some good questions here, some real application for some conversations that we've had with different use cases as well. Before we jump into Q&A and discussion, let me just mention a welcome to anybody who's joining in late. A reminder that we're recording this for later viewing. So let's go ahead and start. Unmute to ask your question if you would like. You can also send a question to me through chat. Ahmed can access that chat tool as well. So let's go ahead. We have about 20 minutes or so for some good Q&A. Go ahead.
Hey, David, this is Hal Johnson with UTA.
Hey, Hal, you go ahead. I appreciate your joining us. Go ahead with your question.
Yeah, thank you. We've been running a small fleet of battery buses for about a year and a half or so. And one of the really interesting things they've seen with the operation of the vehicles is with the changing of the weather, there's significant changes in energy consumption on the vehicles. So, for example, our battery bus in really ideal conditions and no heat or no AC will use about 1.5 to 1.8 kilowatts per mile. And then when we're producing heat on the vehicle, it's 3.5 kilowatts per mile. So I wanted to, I guess the question would be, kind of how do these optimization strategies fit with such great variability on the use of energy on the battery vehicles?
Yeah, I think this is a really good question, and I think I agree with you also. There are wide variation in this number based on the operation, and I think the tool that we have, it accounts for auxiliary load. So if we have numbers for these loads, so we should be able to run several scenarios accounting different numbers, and I'm sure at the end we're gonna have range of solutions. So maybe for each scenario, instead of saying, for example, 100 kilowatt a charger or 70 kilowatt hour battery, we're gonna see a range from 100 to 120 kilowatt charger, and maybe a battery from 60 to 70 kilowatt. So I think there won't be one solution that is gonna fit for each number, but we might have a range that we can choose or we can work within this range. And we try to do this in this study by using the real world data that we collected from the vehicle. And actually also we have some challenges to define a specific number. For example, the data doesn't tell us if the vehicle is on or off during the stop. So if the vehicle is on, this means that we have more consumption, more auxiliary loads. If the vehicle is on, this means that we don't have too much to draw. And in order to get a kind of a better estimate, we investigated the two cases, and at the end, these are the two extreme cases, and the solution has to be somewhere between these two numbers, and we average the two cases at the end. So yeah, I agree with you. There are uncertainties in terms of auxiliary load estimation, but I think running some sweep analysis and sensitivity analysis for several cases will help to try to address this uncertainty. I hope this is answer question.
Thanks, Ahmed. Hal, unless you want to follow up there, Ahmed, I did have another question. Was exactly the same come to me from another cold weather climate. So if that's something that you do eventually update in this model, it would be of interest to several of the different attendees here today. So there's another, let's see, Mike Volb with Stantec. I see you unmuting. Why don't you go ahead and then I'll come back to the chat.
Oh, great. Thanks, David, and good to see you. And Ahmed, great presentation and certainly relevant today. I didn't notice it in the slide deck. You mentioned in the test setup, but how long was, I guess, the dynamic section in the trial, and what was sort of the vehicle transfer rate or the anticipated speed of the vehicle?
Okay, yeah. Yeah, related to the first question, how long the wireless charger? Is this the question?
Yeah, for the dynamic section, because I think you looked at a quasi, which assuming would have a static section where it's inductively charging, sitting still, and then there's a section probably with dynamic charging where it's traveling along a section of electrified road. I'm assuming. So I was curious for this exercise how long that section of road was, and then what sort of speed of the vehicle was assumed, which would give us sort of the transfer rate.
Yeah, I think I can easily answer the second question about the vehicle speed. As you can see, it shows a maximum of, I don't think this one, but I think this one, a maximum of 10 miles per hour.
Perfect.
No, this is a very low speed operating speed, but I think this also align with the scenarios that we are talking about. It's a university. Also, and at NREL, for example, we run several of these buses, and drivers are not allowed to exceed 15-20 miles per hour. So even though the speed is very low, but I think we expected to see this operation in some places. Related to the other question of the length of the dynamic. So as you can see, in this case, it's an optimization problem, and the optimization has to choose. We open the solution or the search space for the optimization to choose between either to cover the entire road or to cover 10%, 20%, 1%. So there is no our limit for the dynamic is the entire route. But at the end, the optimum solution was basically match exactly with the quasi-dynamic. So since one charger at the stop is enough to provide the power that the vehicle require, so there is no need to electrify any of the road. As you know, the energy that the vehicle will receive if it's in a stop will be much higher than the energy that it will receive if it's moving over a wireless charge. So always we see and actually this is not the first case that we run. We run other cases at Greenville that has much longer route than this one, and also another scenario for an automated mobility district. And we consistently see this number that if you are able to charge your vehicle at the stops, so it doesn't make sense to try to use dynamic charging and electrify the road, as this basically is going to be much more cost than a static charge.
Thank you. So just in follow up, I guess that means you really only we're looking at one static charger in this scenario, which was an inductive charger. Is that correct?
Correct. Yeah.
Okay.
And this is a solution that's shown here.
Right.
Yeah. Thanks, Ahmed. Mike, again for your question, and I think that makes sense, and in particular with this given use case. I would be interested to know. You can come back to my question later, but I'd be interested to know what plans you have to extend this study for even longer, corridor road segments. But before that, let me get to the question here on chat. This is from Raphael with Magment. What's the reason for the 100 kilowatt charger for the semi-dynamic? Probably while you're still on the slide, we can just stay here. Wouldn't a smaller charger be enough? And then a related question, how long does the autonomous vehicle stop at that station, at that charging station?
Yeah, okay, that's a really good question. Related to the first question, why we need 100 kilowatt? Basically, we have a kind of a very restrictive constraint in this study is to try to achieve charge sustaining operation. Charge sustaining operation mean to have almost near flat set of charger profile, and this will allow theoretically allow unlimited driving range. So you might need to worry. You don't have to worry about range anxiety, or you don't have to stop the vehicle for recharge and interrupt the service. So with this hard constraint and with one charger in the route, the power level that can provide or can compensate for the energy consumption of the vehicle, it requires 100 kilowatt. So it's not something that we choose, but it's at the end we need to the energy consumption due to driving. We need to compensate this energy by the power or the energy that will come from the charger. And of course, the energy that will come from the charger depends on the power level and the time that the vehicle is spent at each at the charger. And in this study, we didn't want to control this time. This time at the end will be defined based on the transportation mode. It's not something that we choose. That's why we rely on real world collected data. So we don't have to play with this time to try to reduce the power level. Does it make sense? So we can provide the vehicle need at the same time. We don't want to impact the performance of the vehicle.
Okay, so related then to that, let me, great question, follow-up question from Karam here, Karam Afridi from Cornell University. What made the battery come out smaller with the single quasi-dynamic IPT charger versus two quasi-dynamic chargers? And his comment is, I would have expected the opposite with all else being equal.
You know, I never think of this question since really the two numbers are very close, 28 and 29, and basically the solver that we have in this optimization is kind of nonlinear. We use genetic algorithm to generate this number, and basically if anyone familiar with this algorithm, he get to know that if you change the setting, the initial setting for the algorithm, you're gonna end up with different solution. So I believe this number it's because of the nonlinearity of the solver, but it doesn't have a technical meaning. I think so.
Okay, great. And I might even suggest Karam, you and Ahmed could get together at some point after this and kick that one around a little bit more. Okay, we have a few more minutes still, 5 minutes, 10 minutes or so. Why don't we open this up and get some more questions? Please feel free to unmute your mic and let's keep this going. Good discussion.
Dave, I think you have also a question related to extending the study. Would you like to?
If you want to take that, sure. I guess really the question is, what are your plans for expanding this study for a much longer roadway section, or like a transportation corridor, whether that's on interstate and expressway, municipal routes, whatever.
Yeah, great. Yeah, I think I think you are aware. I'm not sure if you are aware that we are working in a project that is funded by the Department of Energy, and this project target high power dynamic wireless charging on primary roadway. And the first year of the project, we try to plan for the system before we start building the hardware with our partner at Oak Ridge National Lab and Idaho National Lab. And as output from this project, we end up with a tool that can work with a large scale deployment of the system. As I mentioned in the presentation, if we are targeting a city or a state and we want to decide where to place the system on roadways and which roadway should we electrify, and where to place the system in these roadways, what is the power level, what is the length at each location, and how this system will impact the travel performance if we are talking about intra-city travel or intercity travel. So the tool has the capability to answer, to provide answer for these questions. So I think this will be the extension for this work, going from a simple scenario like fixed route shuttles or transit buses to large scale scenario with more challenges related to uncertainty, where the vehicle drive, where the vehicle travel, and I think the result from this project, it will be published soon, and yeah, I think this will be a good extension for this study.
Yeah, I look forward to that. And I think that you had planned on adding the variability of utilization as well, right? Number of vehicles as well as different vehicle types.
Correct. Yeah. Yeah, actually, we are considering if we have a light-duty vehicle, so we see variability in the powertrain model, if it's a compact vehicle or USV. Also, actually, the challenge part, if we have this system on public roadway, so we expect all the vehicles should be able to use the same system. So we are kind of targeting the extreme cases, which is light-duty vehicle, also a Class 8 long-haul truck. So the two vehicles, these two completely different vehicles, should be able to use the same system on the roadway.
Great. Look forward to that expanded study. Look, we have a few more minutes still here. Let's go ahead and open this up for additional questions.
This is Prabhakar.
Prabhakar, go ahead.
Yeah, thank you, Ahmed. The question is, did you do any sensitivity studies such as, I'm not sure what the price premium on the battery was for having the fast charge capability versus not, and the sensitivity on the charger cost as the charging power goes up and so forth, because those are going to be changing, and it would be good to know how the solution varies with those changes.
Yeah, correct. And I completely agree with you. And we did some kind of sensitivity, but it's really, you know, it's really hard to try to study wide range of all the variables, since we have too many variables related to cost. We have cost for power electronics, cost for material, cost for construction and battery and vehicle assembly and so on. Also, we have other variable related to the vehicle. So what we did at the end, we ran two cases, which include two different assumptions. One assumption that account for present day cost for material, power electronic, construction, battery. And this number we can easily, it's not very easy to get them, but we have also to do some assumptions and to reach to our partners to get better idea about these numbers. And also after that, we run another scenario, which is a different number for cost and different assumption for vehicle. But at the end, as you can see, both of them show with same attitude. Even though we see lower battery size, for example, and lower charger power level, but both of them see the same attitude in terms of charge sustaining operation for the vehicle, and also in terms of comparison between the three technology. Does it make sense?
Thank you. Yeah.
Sure.
Yeah, great. Thank you. I suppose perhaps related to that, another question on chat here, Ahmed from Ziki Song here at Utah State. In the DC fast charging case, is there a reason for the assumption of the battery carrying a 12-hour battery? Could that be a smaller battery, for example? I suppose it's a variable that you could put in your model, but I'll let you address that.
Yeah, I think that's really a good question, and I think it can be added as a fourth scenario. But in this case, we will need to interrupt the operation of the vehicle for 15 minutes or 30 minutes to recharge, which I think in this case, I feel like it's gonna be unfair comparison if we try to compare this with other technologies that provide the service without interrupting, that provide the power without interrupting the service. But I agree with you. I think this can be added as a fourth scenario to allow a smaller battery at the same time to charge this battery several times during the day.
In particular on that smaller route or that shorter route.
Yeah.
Yeah.
Right.
Yeah, thank you. Yeah, that's really great, because the reason I ask this question is you think about some city like Park City, they have relatively shorter route for their bus. So they actually have this fast charger installed at their terminals, and then yeah, they only carry a small battery, and then the every loop they can charge the battery. So that's why I'm asking this question. So whether it's possible, very similar to your quasi dynamic charging case, just install the fast charger in a terminal, and then whenever they pull into the bus station, they can just charge while they're waiting there.
Yeah, correct. I agree with you, but also I think in these cases, if you have high demand, high transportation demand, so you might end up with adding more vehicle in order to compensate for this interruption, right? So if we're talking about 20 minutes, 30-minute charging time, so you might end up with increasing the fleet size in order to compensate for this interruption.
Yes, I agree. But the other thing you might want to consider in future studies, for DC fast charger, the power could be much higher than the quasi dynamic charging. I think you assume 100 kilowatt, right? Currently, for a lot of the DC fast chargers used for buses, they can go up to 300 or even 500 kilowatt. So that's another consideration. The charging time could be much shorter than the quasi dynamic charging you are considering right now.
Yeah, 100 kilowatts, this is for the quasi dynamic, but for the DC fast charger, we have 250 kilowatt. And why we limit this power level to 250, as we have constraint related to C rate. We cannot go, as you know, the battery cannot handle too high C rate. So we have a C rate limit. I think it was 4C, and we were working within this limit. So we have also a limitation to go higher than this power level.
Yeah, thank you. Yeah.
Good discussion. It's one that I think we ought to continue. And by the way, good engagement all the way through. This is where I hate to shut it off, but also where I'm thrilled that we've had a conversation that pushes us right to the end. Ahmed, let's let that be the last word. Thank you again for the presentation. As we're wrapping up here, just a reminder that this presentation will be available later on the Aspire website with member login access. We're just finishing up the setup for the new Aspire materials library on that website. These brown bag sessions and access to these video recordings are a valuable center of member benefit. So the next Aspire brown bag will be presented at 4 p.m. Eastern on Wednesday, December 9th. That's Dr. Sam Labby, Professor of Civil Engineering at Purdue University and Associate Director of the Center for Connected and Automated Transportation. Sam will present on minimizing urban vehicular emissions through efficient design of electric charging station networks. So with that, that concludes today's brown bag. We thank you again for joining us. Ahmed, once again, we're clapping for your presentation. Hope you enjoy the rest of your day, all.
Thank you, Dave. Thank you, everyone.
Thank you.